Hi, and welcome to the summary and review for this very first unit about scientific methods. I want you to remember how we started our course and how we made a pendulum go back and forth, and what did we do? First of all, we said, well, what can we observe about it? And we talked about this back and forth motion, and we gave a name to it, period, and we observed a whole bunch of things. And then I changed the question a bit and I said, so what could we measure? And so right away we talked about, well, the period, and how would you measure it? Well, you'd measure it with a stopwatch. What else could we measure? We could measure the angle of how much we started it from. I called that the amplitude. And how would we measure that one? Well, we could measure it in degrees using a protractor. We also talked about how many grams, what the mass or the weight was. And to measure that, we had a scale. And then we moved on, and I guess the bulk of our unit was about this relationship idea. It really boils down to how does the independent variable depend, how does the, I should switch these around. How does the independent variable affect the dependent variable? How does the dependent variable change when you change the independent variable? So which one is which? The independent variable is the one that you can change, and the dependent variable, which is the one that changes as a result. So when we look at these three, period, amplitude, and mass or weight, well, the ones that we could change were the amplitude. We could decide where to put it. We could also decide what mass to put on, but the period depended on the other ones. So that's the way we set it up. So in our relationships, we could say, well, we had amplitude versus period. Usually we write the independent one first and then the dependent one second. Then we checked the mass or the weight versus the period. And what was the other one? Well, I guess we had length as well, didn't we? So the length of the string versus period. So we actually explored three different relationships, right? And the next step when you collected your data was to put the data you collected into a table. So say looking at this first one here, our table of data, well, we'd have, those same things. You'd have the amplitude, maybe I'll use the letter A, and usually we say what the units are, and that would be degrees. We'd have the period, and probably in seconds. And you collected a bunch of data, and I don't know, let's say that the data was kind of almost the same. And then we would say, hey, what would that look like as a graph? This one was pretty easy to graph. And we would put the period over here, and we put the amplitude over here. This is in seconds, and the amplitude degrees over there. And we end up getting, well, most of the dots were, say, around one spot. I'm putting it happened to be in my made up data around 2.1. And we can draw a line of best fit to fit the data. Maybe I'll put another dot down there. And then we could make an equation out of it. And so in this situation, if we say, okay, if it's a straight line, here's our kind of basic template for a straight line. In this case, the slope, if it's horizontal, is equal to 0. So that means that this part here turns into 0. The k is a 0 value. And then 0 times whatever x is still 0. So really, y is equal to b is what it boils down to. Y in this example is period. And the b value is 2.1. And as you guys learned during the unit, is when you write down the slope, you also include the units, and when you write down the y-intercept, you also write the units. So this is what it looks like. You'll notice that it doesn't matter, the amplitude is no longer in that equation. So no matter what the amplitude is, the period is always 2.1 seconds. You could write this out in words. You could say, well, there is no relationship. that's one way to write it. You could also say changing the amplitude has no effect on period. So that's how the first one went, that's how the second one went, and the third one was a little bit more involved. So the third one would be an example where you had to spend a bit more time to figure out that equation. So here is an example where I've got some data here in a table, and the first time that we graph it, so if we just type that in, we get logger pro to graph it, and it seems to me I kind of took the picture, I didn't quite capture it properly. I'll just label that side mass in kilograms, and I look at that and I say, it could be a straight line, but it also kind of looks like a curve. So here's what we learned to do. We learned to say, okay, which one of these known graphs could that one be? And it seems to me that one looks most like a B. So this is a skill that you're going to have to know, and I know it looks tough right now, but of these A, B, C, D, E, those 5 here, I want you to actually kind of know what these relationships are. So this is one that we already talked about. This is like the no relationship. The formula would just look like y is equal to b. And I think I'll switch to blue. The other one that's kind of easy is this one, y is equal to kx. And if it's a little bit higher, like that, then it would be y equals kx plus b. So you know what I'll do is I'll go and I'll say this blue one is y equals kx plus b, and maybe I'll put I don't know, red over top of this one like that, and I'll say, or you could just have y equals kx, right? A couple of different variations on that. Well, which other ones? This one here, let's just look at that. How could we remember what this looks like? Well, if you analyze this, as x gets larger, as I move further to the right, so, you know, at this point has a small x value, this one has a larger x value. As x gets larger, the y gets smaller. So that one goes up and the other one goes down relationship looks like this. Y is equal to, there's a couple ways to write it. You could say k over x, or you could say y is equal to k times 1 over x. It doesn't matter too much. Mathematically, it's exactly the same. What do we call that relationship? Well, I would say y is inversely proportional to x. Essentially what you do is you take this equals k business, inversely proportional to 1 over x. I'm sure somebody caught me on when I did that. You take that equals k part and you can, let me just back up. I could say inversely proportional, and I hope I'm not confusing anybody. I could say inversely proportional to x, or another way of writing it, y is proportional to 1 over x, okay? So these two ways of talking about it is the same thing. Y is inversely proportional to x, or y is proportional to 1 over x. Okay, so looking at that second way, when I say that equals k business, I use the word is proportional to, and I take out the equals k and change it to is proportional to. That's sort of like the template for it. Okay, so now hopefully you're okay with A, E, and D that we've done so far, but looking at B and C. Well, if I think about the way this line starts off in this direction, if it was, how could I turn this curved line into this blue line that I've just drawn? Well, I would have to sort of help out x a little bit. I would have to, like if this was a string or something, I'd have to take this and kind of pull it that way to make this line. So that's kind of one mental model I find that helps for students to remember. So if you think that, hey, I need to kind of help x out. Okay, I had a little weird crash, but I'm back. So if I need to help x out, you can think of y is equal to kx squared. So by squaring x, I'm kind of stretching it more to the right. Or another way you can look at this is just remember, if you're doing grade 11 pre-cal and you think, oh, this looks a lot like your basic y is equal to x squared, which is a parabola. It looks like this. This looks like the right-hand side of a parabola, is another way to think about it. So how would we write this out as a proportion? You could say y is proportional, I'm going to write it all out this time, proportional to x squared. B, it's the opposite way. Instead of it curving this way, in this case, if I start off sort of like the straight part of the line in the beginning, I would have a line like that. And I mentally, again, I can say, well, I kind of need to help y out. I need to pull that string up more. So I could say here, y squared is equal to kx. Or another way of saying this is y is equal to the square root of kx. So I'm going to mostly use that first one, and I'm going to say that y squared is proportional to x. So hopefully you can use those tips to remember them. So during an assessment, during a quiz or a test or something, I would like you to be able to know those 5 kind of basic graphs. Okay, so looking at this question, well, let's say we are at this point and we say, hey, we think it's a curve, we think it's B. So instead of graphing mass versus time, we're going to graph mass squared versus time. So this is what we get using Logger Pro. You'll see now they're graphing mass squared versus time. Some interesting things happen. First of all, you'll notice that the units get squared as well. And once you do a linear fit, you're going to say, wow, this correlation is 1.00. So the rule is closer to 1. How do you know which relationship fits best? In other words, the first one that kind of looked like, this, was that the best one, which was y versus x? Or is this one better, y squared versus x, where they're all in a straight line? Well, sometimes it's hard to tell. This one's pretty straightforward, but otherwise you can look at the correlation. So closer to 1 is better. And the other kind of rule, and I did not mention this in this class, or I don't think I did, is kind of a shorthand that we use in science sometimes. It's called Occam's razor, and the other one is simpler solution is usually the right one. Right? So if say 2 students come in late and one student is lying and one's telling the truth and you don't know which one to believe, and one person says, oh, the reason why I came in late is because there was a UFO that stopped, took me away, we did time travel, I experienced all these things, and I came up and then I was sort of in a daze, so I showed up late. And if the other person says, well, I slept in, it's probably the simpler solution. So if you have something really, really complicated, if you find you have to like cube y and square x, and then finally you get something, but it's pretty well the same as just y versus x, go with the simpler one. Now, I want you to note that both graphs are correct. So if you have, this one, y versus x, and it looks like this, that is the correct graph for that relationship. When we say y squared versus x and we get a straight one, these are both right. They're both true. This shape of a graph is true for y when we graph y and x. This graph is true as well. We can say the relationship is y squared is proportional to x. This is a true statement for this one. It's a true statement for that one. So the second one, this way of graphing it is more useful when you need to find the equation. This original one is more useful when you want to look at and say, well, what happens as x increases? Well, x increases, y increases, but not as quickly. It's got that curve shape to it. Here it's hard to sort of interpret because you say x increases, yeah, but y squared increases. What does that mean? So our last step was to make an equation. So for this one, what would it look like? Well, if I start off and I say, here's my basic template, y is equal to mx plus b. Right now in that graph, what is the y value? The y value, the y is mass squared. So the variable is mass, the unit or mass squared, and the units is kilograms squared. So here I'm going to say, instead of y, I'm going to write m for mass squared is equal to, now this m, or actually let's switch to k. That k value is the slope. Looking at the slope, here is the slope, 949.2. And we include the units for the slope, kilograms squared over seconds. And the x value in this case, we don't use the units, we want to use the variable, is time. So I'm going to put a t here. Now this kind of looks complicated with these units in that letter, so I'll put parentheses around there just to keep it neat and tidy. Plus the y-intercept. Well, what's the y-intercept? I got such a thing. Now the y-intercept is 0.86, and you'll remember my shorthand solution here is if I say, well, you know, half, like the median of the y value, so this is, you know, 3,000 approximately is the median, 20% of that. So what's 20%? 20% of 3,000. Well, 10% of 3,000 is 300. 20% of that would be 600. So if it's less than 600, we can pretty well get rid of the y-intercept. Well, it's at 0.8. So it's so close, I can just count that as 0. So I'm just going to leave that off. So there is an equation. And that was the main thing that we practice. And I just want to say this is the basis of science. Like the unit is called scientific methods. And what is science? At its basics, science is observing, measuring, and finding relationships. And once we found that relationship, we're learning multiple ways to talk about that relationship. We're able to display it just with raw data tables. Quantitative means just with numbers. We're able to use graphs, or so a graphical way to show the relationship. Equations are very powerful, but they're not the only way. As you can see, this is just one of 4 ways, or we can do it in words. So how to get the equation, that's what we learned. What can graphs tell you? You're beginning to learn that y-intercept and slope is more than just something that you use in math class, that they can have meaning, and this was for one of our worksheets. So in this case here, if we're talking about cost versus music, and the units are dollars and compact discs, the y-intercept, I think, was the $3.6 is the base price. Perhaps could be from shipping. We don't know. We're just kind of taking guesses. Before you add $7 for each compact disc. So the slope here is the price per CD, right? And it's $7 per CD. So $7 per CD. When you get those units, you can think, how many dollars for one CD? So whenever you look at this ratio here, and you got something in the numerator and something in the denominator, you can say, well, it costs $7 for every one CD. It's a good way to talk about it. Now, we're not going to do this in this unit yet, but later on, the third thing we're going to look at is we're going to say, does the area, and by area I actually mean this area here between the x-axis and the line, does this area mean anything? And I don't think it means anything for this case, because let's think if we multiply the units together, dollars times the number of CDs. I don't think that dollars times CDs doesn't really have any meaning to it. So sometimes is meaningful. Sometimes means something. So at the end of each of our labs, when we've done an equation and we've figured this all out, we're going to look at area and see whether we're going to use it. We can use CDs for calculations as well. So, and that's the nice thing about equations, is now that we have this one, we can say, okay, y equals kx plus b. So in this case it was cost is equal to $7 per CD times the amount of music plus $3.6. You could say, well, what happens if I order 10 CDs? So then the cost is going to be equal to $7 per CD times 10 CDs plus $3.6. Something neat happens here with the units. The CDs cancel each other out, and we get $7 plus $3.6. So what is that? $10.60. Pretty straightforward. The other thing we talked about is proportional thinking. So I'll just really quickly fill in these values. So here's a couple questions we can answer. Tell you what, why don't you hit pause and see if you can answer these, 4 questions, and then you can play again and you can see how you did. Okay, so press pause now and see if you can answer those questions. Okay, so the first one is the relationship between mass and period. Well, we found that it didn't matter what the mass was. The period was pretty well always the same. So we can say, I don't know how you answered it. You could say A, or you could say Y equals B, or you could say no relationship. Many ways to answer that. If I double the mass, the period stays the same. Next, if position is proportional to the square of time. Here, I'm going to write this up. If position is proportional to the square of time, it's kind of like this one. If P is equal to KT squared, which one would that look like? That one would look like this, that one there, okay? What happens to P if T is tripled? Okay, so if I multiply this times 3, what's going to happen to this? It's going to get multiplied by 3 squared. So the answer is multiplied by 9. Energy is inversely proportional to radius. Okay, so E is equal to K over R. What happens to E when R is halved? This is a little tricky. I'm ending with a little bit of a trick one. So if I say this is multiplied by a half, well, remember this is like the inverse relationship. So if R is getting smaller in this case, E is going to be getting larger. So this one is, if this is in the denominator, I'm multiplying this by the reciprocal. So if this is getting half, this one is going to get doubled. Instead of 1 over 2, you can think of it as 2 over 1. So the answer would be E, energy, is doubled. Or you could say, multiplied by 2, something like that. Okay, hopefully that was helpful for you. Yeah, we are at the end, and I will see you in class.